In hopefully this short segment, we're going to look for Poisson. This is Stats 1. This is Bill Foote. We're in Lecture 4, Counting Raptors and Laborers on a Corner. And in the first part of this lecture, we did the big build-up, built the simple model, got to the point of inference. We're going to go back, and now this is an optional piece for people who want to do data science light. For those who are interested in data science, it gets you into why the Poisson likelihood actually works. The thing we're going to solve for is this equation. Probability of x at t equals e to the minus lambda t to the x factorial. We're going to come up with this formula. It's instructive. It uses a technique called recursion. It uses another technique called solution of a fairly simple differential equation using another concept from calculus called the product rule. And we all might just go back in time here if you've had any kind of calculus. Suppose y equals the product of two things, u of x and v of x. It might be x squared times the sine of x. Ha, trig. Yeah. Anyways, data science uses trig. Okay, we're not going to apologize for any of that. And we want to find out dy dx, the derivative of y, the rate of change of y with respect to a very, very small change in x. And the product rule basically says, I'm going to not use the x's there, u dv dx plus v, got it, du dx. Now, common sense. Any change in y might be revenue, u might be price, v might be quantity. There are two sources of the way R might change, revenue might change. One is for a level of quantity. Well, let me do it using the UVs that I've got there. For a level of price, what is the change in quantity? And for a level of quantity, it'll be the level of quantity due to a change in price. Nearly every sales department uses this idea. It's a decomposition of R into Q and P. And we can have equations for P and Q and so on and do all sorts of interesting things here. But it's the product rule. And we're going to use the product of two things. Just jumping right ahead, we're going to let U equal e to the lambda t, not minus lambda, and v equal to the probability. I'm not going to use PR. I'm just going to, I better use it, of x at t. So that the change in uv equals the change in e to the lambda t. This is all preview. That particular weird expression is that? And we're going to see it's going to be equal to e lambda t times the change in PR xt plus PR xt times the change in e to the lambda t. Now, one more calculation. The derivative of e to the lambda t, in this case, t is the small change as opposed to x, is equal to lambda e to the lambda t. Okay. So pretty straightforward. This has a special name, by the way, but we'll leave that off for the moment. And so this total derivative of this product of u and v equal e to the lambda t change in this probability. It's one contribution to the total change plus the probability xt lambda e to the lambda t. In this case, it's dt. We also need dt over here as well, because this whole thing was divided by dt. Okay, so just so that we know that, and I should have put that up here. Oh, I'm not a mathematician, a statistician, or anything, so I do use this stuff all the time. Yeah. And sometimes you forget a little minor mathematical detail, which is pretty important actually. But when you take the integral, and we're going to take it from 0 to some number, we're just going to call it t, of d u d, which is just the same as taking the integral. We're averaging, in a sense. We're actually finding the area in actuality over a small over an interval of, and I know I'm in deep trouble here with using t and tau and all of that, but don't worry, it's not going to change any of the results. Okay. These two things are simply equal to e to the lambda t brx t. At 0, those things are zeroing out. And then this becomes the derivative of e to the lambda t d pr xt plus this. Actually, lambda can come out. The lambda t dt. Okay, we can do derivatives here, but getting to this integration is the rub. And that's what we will solve for. Just wanted to show you that we can use something. The u, e to the lambda t, is called an integrating factor. And you can figure out how old I am by this next reference. All my knowledge of this comes from notes from many, many, many years ago using George Thomas's Calculus and Analytical Geometry, 4th edition. I think that was 1968. It's one of the last chapters, and we all did it. We're going like, why do we want to do that? Well, it was a space race at the time. Everything was about physics and orbital mechanics and launching. How much fuel do you need to launch something into an orbit, and to go to the moon and back, all that kind of stuff, right? And all of this comes as part of it. The Poisson distribution. Okay, very important part of it. Geiger counters, all right? Radiation. Now, if your company owns a uranium mine, you're going to want to know about this kind of data analysis. Absolutely. See if you glow in the dark. We're going to be solving for this expression. And this is going to go in a couple of steps. First, the development of how we get a relationship. And it's very similar to what we did in part 1. The first thing we do is we have a branch. You can either have a particle emitted or no particles emitted. We can have a laborer show up, no laborers show up. We can have a credit default, no credit default. That's going to happen with rate lambda delta t. And in our example, delta t was, remember, 1 over 3,600. Okay, very, very small number. Lambdas turned out to be from 3 to 27. Okay, so you can figure that this can happen. And you can figure out events that are rare and not rare. 1 minus lambda delta t is the other probability, because these two probabilities add up to 1. Okay, they're also the probability, we give them a official name, the probability of 1 in a very small time interval is lambda delta t, and 1 minus this, the probability of 0 in a very small time interval, like 1/3,600th of an hour, is equal to 1 minus lambda delta t. We're going to use both of these in our derivation. And that's where the e to the minus lambda comes from. We're also going to use the idea that we're going to use this idea from lecture 1. And we can actually get this from a differential equation and solve for it, or we can use Jacob Bernoulli, his experiment, where he finds that E equals 2.718, I think it's 2, and so on and so forth. Continuous compounding. Not a physics experiment. A finance experiment led to E. I remind all my physicist friends of this every day. Okay. All right. As much as I love physics, Halliday and Resnick was my physics approach. So how can we get at the end X laborers, X particles emitted, X defaults, X vehicular contacts, otherwise known as collisions, at the corner of Muir and Westchester Westchester and Crosby and Edison Avenues. Okay, how do you get that in the Bronx at a particular point in time? Noon. All right, you got a lot of cars going back and forth. Just a few actually crash. It's mostly zero. So to get X, we can start out with X arriving at time t over small time interval. End of the small time interval is delta t. We can let that interval get ever smaller, but I think this is pretty small. Yeah. Okay. At this time, we can have X arriving, and X plus 1 occurring in this time interval with probability what? Lambda delta t. Oh, no, it's already there. So nothing arrives there. And that's probability 1 minus lambda delta t. There, catch yourself. Okay. And you get X at the end. Okay. Or you can have X minus 1, whatever X is, at the beginning. You can have an event occur, somebody arrives. So X minus 1 plus 1 gives you, again, X at the end of the interval. So we have two ways, two probabilities. And this top way happens with lambda delta t. Now, these are mutually exclusive, completely exhaustive. It's all of them, and they're mutually exclusive. You got to have both conditions occur. They all end up at X at the end of this very small time interval. I remember we were modeling this. Here's T. Little time interval. T plus delta T, as you can either have 1 come in or none come in. Okay, if you have 1 come in, and they all give you X, so you can either start off with X minus 1 come in, you get X, or none remain. Okay, that's the little bit of things going on, and that's all that's going on. Little diagram there. They all end up at X. You see a little relationship going on here. We have this relationship going on here. So what's the probability of this top line here? This is the probability that you start off with X minus 1. So you have 30 labors minus 1, 29, okay, at time t. And that's a both and relationship. It's both this occurring and this occurring at delta t in the transition. So it's the probability of 1, and that's a very small time interval. And we know what that probability is. Mutually exclusive, completely exhaustive, we add them together. These are either or logical statements. Probability of X at t. That's the probability of nobody coming in, no particles being emitted, no defaults occurring. We get the probability of X at t plus delta t. Okay. we have an equation. We have a recursion. Let's just put this down here and let's not get too busy. We have the probability of x probability of x again. I think I had x minus 1 up there. At t times that's lambda delta t. Pop that in there. That's the probability of x also at t, and what was that probability? Nobody's coming in again. This one, probability of nobody coming in is 1 minus lambda delta t. By construction, by assumption. And so we got that. Well, what can we do with this? We could rearrange this, and you can see that we can take this term and bring it over here. Okay. And then we will have this term and this term over on the right-hand side. Let's do that. We have the probability of x plus delta t minus the probability of x and t. That's just this multiplication here. That is what that is. So we just bring this, subtract that from both sides. And I hope you see a calculus thing begin to occur. Now, I'm not using a notation like O of delta t, which is a function such that the limit as delta t approaches 0 of O of delta t divided by delta t equals to 0. I'm not using that notation here. I'm assuming it, of course. I'm not the mathematician, but I'm a physicist. I'm an economist. Okay, that tells the whole story, right? I'm a social scientist. I almost don't like the word science in there, by the way. We'll have another discussion about that another time, about hermeneutics and how to interpret all of this stuff we're doing here, which we call science. Okay, which is also why I do Bayesian, because it's a little bit more like the way consciousness operates my mind. So, okay, I got this, and look, it's a difference in t, in delta t, and that's the delta t difference in the probabilities occurring. Now, you go back to the diagram to understand that. We have a differential probability going on here and here. This is the one we're looking at right now. This differential probability of x at t versus t plus the transition, somebody arriving or not in the very next second of that hour. Okay. And what are we left with over here? We're left with minus lambda delta t p r x t. That's this thing. And we're left with this thing here. Plus lambda delta t times p x minus 1 of t. Now, if we divide this equation, both sides, by delta t, so we do each of these probability statements, and here's a difference. We want to know the difference in this probability going from here to here, still ending in x. That's the difference in that very small time frame. Oh boy, very, very small time frame. So there's a dynamic relationship that goes across time, or if t is the size of a 2x4 and stuff is sprinkling across it, okay, there's a probability of that stuff occurring at different points on the length of the board. And that's how they count black mold, for example, or across surfaces. Okay, it's the same idea. And everything here is, by the way, very linear. We're dealing in very linear space. Okay, we're not doing circles or spheres or ellipsoids or anything like that. Very, 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 because there's very, very small patches of, let's say, a sphere, which looks like a square, right? Okay, that's how simple our math is, believe it or not. And finally, if we take the limit as delta t goes to 0 on both sides, we have the definition of a derivative over a very small and ever smaller, that's what that limit means, as the that 1/3600th interval gets even smaller, and then you can make it even smaller. So things have to be continuously able to be smaller and smaller. Okay, this is going to be equal to, now notice, very conveniently, those little differences go out. 1 divided by the other is equal to 1. Anything times 1 is itself. Okay, we have minus lambda er x t plus lambda er x minus 1 t. And finally, we get the pièce de résistance. There's the differential plus lambda in exactly the same function. This function and this function are the same. Okay, a first order ordinary differential equation, non-homogeneous, lambda er x minus 1 t. So we're going to solve this equation. It's actually not as hard as it looks if we remember how to use this apparatus called a integrating factor. Well, where the heck is the integrating factor here? It's going to appear here. Okay, we're going to eventually have this minus here. So if we multiply everything through by e to the lambda t, if this probability is built off of that, then e to that equals 1. It's going to simplify things tremendously. That's what integrating factors do. But they also do one more thing. They allow us to use this very simple product rule in order to do this and to get to this, okay, with constants of integration, which are going to fall out very nicely. Okay, so that's our next step. And then once we have that next step, we can demonstrate, this is not a proof, it's a demonstration, a sketch of how we get our crazy formula, which is the thing I think we were trying to look for up here in the first place. How do we get this? Okay, now let's just do a couple of iterations here. Let's let x equals 0 first. Now that's this. A small change in that probability. Now, it turns out that you can't have a -1. Just doesn't work out that way. It doesn't solve. So the probability of losing 1, so you start at 0 and lose 1, is like nonsensical. Okay, at any time t. So effectively, what happens to this term? So the nub comes here. What is this? Down here we have lambda probability of -1. Okay, x is 0, -1 in t. But this is impossible. Impossible in probability means 0. So our whole equation here just goes to 0, and we have this lovely thing. Now, and what I'm going to do, I'm going to say PR0t is just equal to p. Okay, just to make life easy. So we have this differential equation for our first time out. We're already running into difficulties here. Equals minus lambda p. Okay. Now, if we divide both sides by the probability and multiply both sides by the small change in t, and I'm not talking like a mathematician at all here. That's how the implicit algebra can work out operator style. I get dp over p equals minus lambda dt. A small change in t, small change in p, probabilities, remember. And this is the percentage change, dp to p. It's like a percentage change. Percentage change is proportional to probability of a success finding somebody showing up, a particle emitting, a particle depositing somewhere, okay, in a very small time frame. Now, if I integrate both sides, now remember lambda is a constant. So if I integrate both sides, on the left-hand side, this is practically the definition of a natural logarithm of p. It's integrating 1 over p. And if I integrate over here, it's minus lambda t. The integral of a small unit of time ends up becoming a line. Small unit of time is like a point. Points integrate, or it's like area, multiply into a set of points, otherwise known as a line. That's what t is. I'll say constant of integration. Call that constant of integration 0 just for the moment. If I raise both sides using the, now e and log, natural log e are inverses of one another. We know that, right? Okay. You just distribute that across. Well, this is just this. Okay, that's a times there. And this is pretty sloppy, I know. But it gets you the idea. Inverses of functions give you the function back. So there's the probability again. So I'm going to write it out so we don't forget what the heck it is. And I'm just going to call this C, constant of integration, e to the minus lambda t. And I skipped a couple of steps, but just not to worry. What is C? We're going to turn out that C is equal to 1. Why? Because the probability of nothing being there at time 0 is certain. Well, if that's the case, then the probability of 0, 0 equals C e to the minus lambda times 0 equals C. Well, C must be equal to 1. So that's our first big win. And we're going to use that in the next iteration. We're going to do a couple of iterations just to demonstrate that our formula will work. Okay. What's our formula up here? This is our whole formula. So let's go back down here. Let's do x equals 1. We have, oops, let's use the darker, there we go, P. 1 T. Ah, you know what this is, don't we? Now you're beginning to see the power of the recursion. We have the probability of 0 things happening, 0 people arriving on the site, 0 things emitting, 0 defaults at time t. It's e to the minus lambda t up here. Okay, we can pop that right in here. How convenient that is. Okay, so just let me put this in here, lambda e to the minus lambda t. And then I'm going to use the magic of the product rule. This basically is the clue that my integrating factor is 1 over this. Okay. I want to eliminate this weird function over here. So I multiply both sides. Light bulbs may be going off here. We're back to little old lambda there. And what is this? That's the product rule. That is the product rule. It is simply the product rule. Okay, Bill, it's the product rule, so what? So it is, this is equivalent to saying d of dt, d over dt of e to the lambda t PR1 t. That's what this whole expression gives us. And of course, e to the lambda t times e to the minus lambda t is 1. And we got lambda. And again, multiply, at least in an operator sense. No, we're not going to do operators here, although that would be really cool to use. The Laplace transform, this is basically a Laplace transform. It was the, one of the motivations for a way to solve these equations rather easily. And there's a generalized version of that. Generalized function, and on and on and on. Okay, good. So if we multiply this, we have d e to the lambda t equals lambda dt. So that e to the lambda t PR1 t equals lambda, integrate this, and because 0 is at the bottom, and sometime t or tau is up there, we'll just interchange those. So we'll just make that the integration, the variable of integration. So tau is going to go from 0 to sometime t. And that's actually pretty important for interpreting what's going on under the things here. And that interpretation, an interpretation world of the math will collide with the reality and the story of people arriving at a service station to be picked up for work by a contractor in a van, or a Geiger counter for that matter. Okay, those are interpretation stories. Okay, and this will be equal to lambda t by the fundamental theorem of the calculus. Okay, the integral of a small t, the integral of 1, actually, it's actually 1 times this, is t. Now, if we multiply both sides by e to the minus lambda, to isolate the thing we are looking for, which is the probability of one person coming in at any time t, we have I hope you're beginning to see something. Divide that by 1. Raise that to the 1 power. Make that 1 factorial. Getting to see something? Well, this, of course, anything like that, 1 over x over x is always 1, right? Okay. Anything times 1 is itself. So we have our second one. We have our first one up here, e to the lambda t. E to the minus lambda, lambda t to the first power, divided by 1 factorial. I just like doing that because you're going to see what's going to happen next. Now we're going to use this. That formula for x equals, what we have, x equal 1, x equals 2. I hope you can see what happens here. That is to that is 2, that is 1. So instead of putting P0t in there, we're going to put P1t into this. And I'm just going to skip all the way down to here. All the way down to here. Okay? We don't have to write all this out anymore, because it's going to be exactly the same thing, but with 2 in here. 2. This changes, though. It isn't just lambda now. It's lambda times something. Okay, when we do the integrating factor. So maybe I shouldn't skip. Maybe I shouldn't skip so much. Well, I can skip part of this. Let's get us down to here. It's going to be lambda times PR1 on the right-hand side. On the left-hand side, it's going to be that expression. Okay, good. Let me bring this down. D, dt, e lambda t by the product rule. Remember, 1 became 2. And this is u, that's v, remember. Equals lambda times this number. E to the minus lambda lambda t to the first power divided by 1 factorial. So instead of this, we get this more complicated with e to the minus lambda t in it. Lambda times that probability. That's okay. Watch what happens. We get multiply both sides by the dt. So we have d e to the lambda t pr equals. Let me just pop this out on this side. Lambda times lambda squared t. Let's bring this out. Those are all constants. T is going to be the thing we integrate again. Okay. Integrate both sides. We have e to the lambda t r 2t equals this. Oh, I forgot. Oh, gosh. Forgot to put this in so that this goes out. Is that right? Yeah, that was right. Okay, why was that right? I did it up here. I multiplied through the equation by e lambda t. The two offset one another, and I'm left up with lambda. And then it's lambda dt. So by extension, same thing happens here. So I'm left with lambda squared t. These e to the minus lambda, e to the lambda t go out. They offset. 1 divided by the other is equal to 1. So let me get rid of this. There we go. Magic of all of this. I am left just with lambda squared. Now, why is it lambda squared? because this lambda gets involved. That's the probability of something happening, because that's the probability on the right-hand side. We had one less over there, and we had x equal 1, so 1 happened, so that's the lambda, and that's how we get that probability. Okay, and but we're integrating here now is t delta, and now I'm just doing integration stuff, where tau again goes from 0 to t. Okay, and the way we do these integrations, it's the antiderivative, right? So the antiderivative of t is t squared over 2. Because if I take the derivative of t squared over 2 with respect to t, that's equal to 1/2 t to the 2 minus 1 power times 2. Bring the exponent down, reduce the exponent, and this times 1/2. That's equal to t. That's what we're looking for. So we have lambda squared over 1. We do the integration, and we get t squared over 2, which is the same as saying lambda t squared over 2 times 1. What is 2 times 1? Well, you know what 2 times 1 is. It's 2 factorial. Multiply both sides by e to the lambda's t, just like we did before. Okay. That's the intermediate step there. And we get t equals 2 e to the minus. You're seeing this thing begin to unfold in front of your eyes. You need to do another one? You can do another one, but again, this is a demonstration. So that, do for n. Does it work for n minus 1? Math induction. It's not really induction. It's deduction based on an assumption. It's still deduction, actually. Induction is the wrong, actually, the wrong logical term. But this will work out to, for any x. Try it with 3, you'll see it. That remains all by itself. You get lambda t x power over x factorial. The factorials come in because you're doing successive recursions on finding out. You're going from a point to a line to a rectangle to a box to a hyperbox. You're increasing volumes. That's what these calculations are doing in probability. So it's asking how many people are coming through the door. You got 5 people coming through the door. 5 factorial is a number of different ways those people can come through the door one at a time. Okay. 5 ways. Okay, in any particular order. Okay. So that's the end of this. And if you can do this, you can begin to think of a birth-death process or an immigration-emigration process where one arrives, nobody arrives, one leaves. And you can begin to build these kinds of models or use somebody else's formula, but understand what went into it, which is the most important piece. And this recursion, we're recursing we're skipping from nobody coming in, we did that, to one person coming in, probability of that, which takes into account the fact that nobody comes in. So this must be at least one person coming in, both and. Down here, nobody coming in and at least two people coming in, at least, because it's now working up to that, or at most two. That's probably more correct. And you keep working at this and you get a better sense, I believe, of what's behind the curtain here. Okay, I'm going to leave it at that. Thank you very much for your kind attention with this non-mathematical, very mathematical it looks like, but non-mathematician, more economist, more somebody who's been doing this a long time and hacking their way through it still, approach. And again, thank you, and I look forward to part 2 if you've seen this, and that will be the Excel implementation.